Okay, so welcome to the next and final part of the lecture series, which is Mechanics 2. So last week we were looking at a few things in mechanics. We were looking at the Suvat equations, and we were looking at centers of mass and centers of gravity. So this week we're going to look at forces. So when we think of forces, we think of a book, a certain book, Mathematica Principia, which was written by Sir Isaac Newton. So apparently, he wrote this book after having an apple drop on his head, but I don't know if that was actually true or not. But in his book, he wrote three laws, and these three laws define pretty much the majority of modern science, one especially. And the laws he were stated was the first law was everybody persists in a state of being or at rest or of moving uniformly straight forward, except insofar is compelled to change its state by force impressed. So if you don't have anything coming in actually to increase a motion, then you'll keep moving at a constant velocity. So if you think maybe if you have a spaceship and it was moving through space, if no external forces were to apply, because in space we don't actually have any external forces, or minimal, then you would keep a constant velocity or a constant trajectory until a force was applied. That's what Newton 1 states. Newton 2 stated the acceleration of motion is ever proportional to the motive force impressed, and it is made in the direction of the right line in which the force is impressed. Okay, so we talked a little bit about this last week, and we're talking about acceleration, but what he was saying is if you have an item which has a mass, its force is equal to the amount that the mass is accelerating to you. So this was his famous law, force equals mass times acceleration. And finally, his third law, Newton 3, to every action there is an equal, always opposed, to every action there is always opposed an equal. Okay, so this is also known in many other ways, as Nearly said it then, each action has an equal and opposite reaction. So a paper I recently wrote on the coefficient of restitution questioned this law, and we were looking at how if you were to throw a bouncy ball, maybe in a simple way, if you throw a bouncy ball against the wall, it's going to bounce because it's exerting a force on the wall, and the wall isn't exerting a force back on it. So that is each action has an equal and opposite reaction, also an equal and opposite reaction. So in mechanics, we can kind of summarize these forces into three categories. So we can summarize them into forces of attraction, for example, gravity and contact forces, weight and forces of attachment, like tension, And in this section, we're going to begin to investigate these different types of forces. So before we actually start to look at Newton 1, 2, and 3, we're actually going to look at vectors, resultants, and components. So a vector. I'm not going to touch on this too much, what vectors are, but I'm just going to give you a brief idea. So a vector quantity is one for which direction is important as well as its magnitude. So it just has one direction. So often we think of speed as a vector because it's moving in one direction. If it's changing in direction, then we wouldn't think of it as a vector. So any vector can be represented by a section of a line called a segment. The direction of the line gives the direction of the vector, and the length of the line gives the magnitude of the vector. So if we were drawing these out, if you were to look in some textbooks, it all depends on how these are drawn. When two or more vectors are added, the single equivalent is called the resultant. So we'll look what I mean by a resultant here, but we won't go too much into the addition of vectors. It's far beyond the scope of this actual module. So anyway, let's think of, let's give you an example. So it says, consider a heavy cart. So consider a heavy cart being pulled along by two angles. Both of the ropes are at right angles to one another. Okay, so it's going to look something like this. The units of force in which the force of the ropes are measured are in newtons. So we have 30 newtons, which is slightly less, and our line is slightly longer, which is 40 newtons. Put our newtons on here. So although the ropes are pulling in different directions, the cart itself will only be moving in one direction. So how can we calculate this? And well, maybe this could be a kind of question that I might ask in the exam. How would we calculate this? And what would be the angle in which this cart might move? And you think if this was a boat and you had two ropes of equal length and two people pulling at different forces. So how do we do this? Well, I can see here that we have something very similar to what we've previously been working on. And we can actually see, we actually have a triangle here. So all we have here is a right angle triangle. And we can see that our longest length is 40 here, and our second length is 30. So what we've been shown previously is that a squared plus b squared equals c squared. Okay, so that's quite easy. We can work out this resultant n just using our a squared plus b squared equals c squared. So we could say that our r is equal to the square root of 30 squared plus 50 squared, plus 40 squared. And if you remember back from a few months, we know that 3, 4, and 5, we would know that R would equal 50 newtons. You can see that into your calculator, but remember, I always use this 3, 4, and 5 when doing these simple examples. So we can also work out the angle in which this would be going. And what we need to do here is bring back our SOHCAHTOA. We have angle here. We know this one 30. We know this one 40. And we want to know this angle. This is our theta. So this is our hypotenuse. This is our opposite. And this is our adjacent. We can say SOHCAHTOA. And we want to find this angle. We only have our opposite and our adjacent. So we know we have to use tan. So we know that the tan of theta is equal to opposite over adjacent, which is 30 divided by 40. Therefore, our angle is 37 degrees. Therefore, what we could state is that this cart is actually moving at 37 degrees away from the center here. So if we were to measure how this was, we would see that this would be our angle. This would be our resultant force. Our resultant force would be pulling it in this direction at 30 degrees. Sorry, the other direction. Where's my? We'd be pulling it in this direction, so perpendicular to this line. This would be at 38 degrees from this normal, and it would also be a resultant of 50 newtons. 50 newtons would be pulling it that way. Okay, so this is just a method and help us take these two directions and convert them into one direction. So, okay, we'll leave it at that, and then we'll go and have a look a little bit about how we can apply this in Newton's first law.